An elderly Inuit man in the Northwest Territories of Canada lies down on a thin caribou hide, closes his eyes in air that sits at -50 degrees Celsius, and sleeps for 8 uninterrupted hours. He wakes with a core body temperature of 37 degrees Celsius, identical to yours right now, sitting in a climate-controlled room. His skin temperature at the hands and feet is measurably warmer when he rises than when he lay down. And here is the part that stopped researchers cold. Giving him a blanket would have made the whole thing significantly harder to survive. For nearly 40 years, physiologists assumed the explanation was simple insulation. Layers of fat, layers of clothing, cultural adaptation in some loosely defined sense. They were wrong about almost every part of that. What the Inuit elders are doing is not surviving the cold. They are using the cold as fuel, and the mechanism behind it overturns something most people believe about the human body from childhood. If you have never encountered this research before, subscribe. This channel covers the biology that medical textbooks still have not caught up with. The Inuit are among the most studied indigenous populations on Earth, and simultaneously among the most misrepresented. Most people picture them as bundled figures in thick parkas, navigating featureless white landscapes, surviving through insulation and willpower. The actual picture is more precise and far more interesting. The Inuit, whose name means simply the people in Inuktitut, have inhabited the Arctic and subarctic regions of Canada, Alaska, Greenland, and Siberia for at least 4,000 years. Depending on the region and the generation, they have lived across a territory spanning more than 5 million square kilometers in conditions that kill unprepared outsiders within hours. Traditional Inuit communities in the central Canadian Arctic experienced average winter temperatures between -30 and -50 degrees Celsius, with wind chill values pushing experienced exposure risk far lower. The sun disappears entirely for weeks at a time. There is essentially no plant food available for months. And historically, the Inuit not only survived this environment, they raised children in it, performed sustained physical labor in it, and regularly slept in it with what Western observers in the 19th and early 20th centuries described, with barely concealed disbelief, as almost no covering at all. The 19th century British naval explorer William Edward Parry, who wintered in the Canadian Arctic in the 1820s, documented Inuit sleeping practices with visible confusion. He noted that individuals who had been performing strenuous outdoor work in severe cold would return to shelter, remove substantial layers of outer clothing, and sleep with what he described as a single thin skin draped loosely over them. He assumed this was explained by the warmth of the communal sleeping space. It was not. Researchers who revisited these observations in the 20th century with proper instrumentation found that the communal sleeping spaces, while warmer than outside, were still frequently below 0 degrees Celsius, a temperature at which an unacclimatized person would experience dangerous hypothermia within a short period of lying still. This is the paradox. When the human body is cold and inactive, metabolic rate drops. Heat production falls. In a sedentary, unacclimatized person, lying still in sub-zero temperatures in minimal covering is a path toward a core temperature collapse. The Inuit elders were not merely tolerating this. They were, by measurable physiological metrics, doing the opposite of what the standard model predicted. The first serious scientific attempt to explain this came from two researchers whose names deserve to be far more widely known. Lawrence Irving, an American physiologist based at the University of Alaska, and Per Skolander, a Norwegian-American biologist at the Scripps Institution of Oceanography, began a series of landmark studies in the 1940s and 1950s that fundamentally changed how scientists understood cold adaptation in human beings. Irving and Scolander used rectal thermometers, skin temperature probes, and metabolic rate measurements, crude by modern standards, but rigorous enough to produce data that held up for decades. What they found was that Inuit individuals, particularly older adults who had lived their entire lives in Arctic conditions, showed a suite of physiological responses to cold that were qualitatively different from those of non-adapted individuals. Their peripheral blood vessels constricted less aggressively in the cold, keeping more blood flow and therefore more heat circulating into the hands, feet, and extremities. Their basal metabolic rate, measured at rest in cold conditions, was significantly elevated compared to control populations. And crucially, they showed a capacity for what Irving and Scolander called non-shivering thermogenesis that was far beyond what the research community had previously attributed to adult humans. Shivering is the body's emergency heat generation system. It is metabolically expensive, physically exhausting, and relatively inefficient. It is also involuntary. The nervous system triggers it when the core temperature begins to fall, and it represents the body losing control of the situation, spending glucose rapidly to buy time. The Inuit elders were not shivering in their sleep. They were generating heat through an entirely different pathway, one that required no muscular effort and consumed fat rather than glucose. The mechanism is brown adipose tissue. This is the explanation that makes everything else coherent, and it is one of the most underappreciated discoveries in 20th century human physiology. Brown adipose tissue, commonly abbreviated to BAT in the scientific literature, is a specialized fat that does not store energy. It burns it directly and deliberately, converting chemical energy to heat with a biochemical efficiency that skeletal muscle cannot match during normal activity. The cells of brown adipose tissue are packed with mitochondria, the cellular structures responsible for energy metabolism, and contain a unique protein called thermogenin, or uncoupling protein 1, which allows the mitochondria to generate heat rather than adenosine triphosphate, the molecule that powers muscular work. For most of the 20th century, brown adipose tissue was considered irrelevant in adult humans. Medical textbooks described it as a structure important in newborns. Infants cannot shiver and rely on brown fat for thermal regulation in the first months of life, but brown fat was thought to be largely absent and functionally dormant in adults. This view began to unravel in 2009, when 3 independent research groups published findings in the New England Journal of Medicine demonstrating that metabolically active brown adipose tissue was present in a substantial proportion of adult humans, concentrated primarily around the neck, shoulders, and upper back. Active brown fat had been detectable in medical scans for years. PET scans used in cancer diagnosis had routinely picked up unusual metabolic activity in these regions, but it had been dismissed as artifact or misidentified as muscle tissue. The 2009 findings opened a floodgate. Researchers began asking whether brown adipose tissue could be recruited and expanded in adults through environmental exposure. The answer, gathered over the following 15 years from studies conducted across multiple countries and institutions, was an unambiguous yes. Sustained, regular, deliberate cold exposure increases both the volume and the metabolic activity of brown adipose tissue in adult humans. The body, when it learns that cold is a recurring condition rather than an emergency, begins building the infrastructure to handle it metabolically rather than defensively. Studies by researchers including Wouter van Marken Lichtenbelt at Maastricht University in the Netherlands and Sven Enerbach at the University of Gothenburg in Sweden showed that individuals who underwent controlled cold exposure protocols over several weeks developed measurably more active brown adipose tissue. Their capacity for non-shivering thermogenesis increased. Their threshold for shivering, the temperature at which the body triggers its emergency response, dropped. They became, in a physiologically precise sense, better at being cold. The Inuit elders represent the extreme end of this adaptation curve. Lifetimes of cold exposure, beginning in infancy, in an environment that provides no opportunity for thermal coddling, produce brown adipose tissue reserves and non-shivering thermogenic capacity that Western populations simply do not develop. When an elder lies down in sub-zero air with minimal covering, the drop in skin temperature triggers brown fat activation. Heat generation begins not as a crisis response, but as a quiet, efficient metabolic process. The sleeping body is not losing the battle against the cold. It is using the cold as the stimulus that keeps the furnace running. The absence of blankets is not incidental. This is the counterintuitive part that most people resist when they first encounter it. A blanket would trap enough heat to reduce the skin temperature signal that activates brown adipose tissue. The metabolic furnace would idle rather than run. The body would generate less heat, not more. The elder without the blanket is running warmer internally, precisely because the external signal, cold skin, is maintained throughout the night. The blanket would be a comfort that undermines the system. There is also a dietary component that cannot be separated from the thermal one. The traditional Inuit diet has been analyzed extensively since the 1970s. Researchers then began investigating what became known informally as the Inuit paradox. It is the combination of high fat consumption and low rates of cardiovascular disease. That diet is extremely high in omega-3 fatty acids from marine mammals and fish. These fatty acids do not merely affect cardiovascular health. They alter cell membrane composition in ways that affect thermal regulation at the cellular level. Membranes rich in omega-3 fatty acids remain fluid and functional at much lower temperatures than membranes composed primarily of saturated fats. The brown adipose tissue of an Inuit elder is at the cellular level, literally built from different materials than that of a person raised on a Western diet, and it functions more efficiently at low temperatures as a direct consequence. This matters for you in ways that are more accessible than sleeping in -50 degrees. The research on brown adipose tissue activation in non-Arctic populations points consistently toward one conclusion: the thermal comfort that modern life optimizes for. Heated rooms, heated cars, heated offices, and clothing calibrated to eliminate any sensation of cold actively suppresses a metabolic system that the human body is prepared to develop and use. Regular, moderate cold exposure means temperatures that are uncomfortable but not dangerous. Sustained for meaningful periods, this exposure measurably increases non-shivering thermogenic capacity in ordinary adults within weeks. The practical application is not extreme. Researchers including Ray Cronies, who worked with NASA and later collaborated with nutrition scientist Tim Ferriss, and Susanna Soberg, a Danish metabolic researcher whose work on metabolic winter was published in the journal Cell Metabolism in 2022, have shown that relatively modest cold exposure produces detectable changes in brown fat activity. Modest practices include cool showers, outdoor activity in cold weather without overlayering, and brief cold water immersion. Soberg's research suggested that approximately 11 minutes per week of cold water immersion, spread across multiple sessions rather than concentrated in one, was sufficient to drive measurable metabolic adaptation in healthy adults. The Inuit elder is not doing something alien. He is doing something human, at an intensity that modern life has made almost completely inaccessible. The system he is running is the same system that exists, in a largely dormant state, in every person reading this. The difference is not genetic, or at least not primarily genetic. Research on indigenous populations who moved to urban environments and adopted Western thermal and dietary habits shows convergence with Western metabolic profiles within a single generation. The adaptation is behavioral and environmental before it is biological. There is one more piece of this story that the physiologists did not anticipate when they began their work in the 1940s. Irving and Scholander noticed something in their data that they documented but could not fully explain at the time. The Inuit elders who showed the most pronounced cold adaptation, the highest non-shivering thermogenic capacity, the most stable peripheral circulation in extreme cold, were almost universally the oldest individuals in the communities they studied. Not the youngest, not the most physically vigorous, the oldest. The implication is that this is not a capacity that peaks at physical prime and declines. It is a capacity that builds across a lifetime of appropriate exposure. The body, given the right conditions, does not stop adapting. It compounds. That raises a question that researchers have not yet answered satisfactorily. If brown adipose tissue activation can be increased in adults through environmental exposure, and if that capacity appears to accumulate rather than deplete across a lifetime of cold exposure, then the conventional model of metabolic decline in aging, the assumption that the body's thermogenic and metabolic systems inevitably wind down with age, may be describing a population that has never actually tested those systems under the conditions they were designed for. We may not know what the upper boundary of human thermal adaptation looks like, because almost no one in the modern world has ever tried to find it. The Inuit elders, sleeping in the dark, motionless in temperatures that would kill an unprepared person within hours, warming themselves from the inside on a diet with almost no carbohydrates, using a fat that medicine spent 50 years insisting was irrelevant in adults. They are not anomalies. They are a baseline. The question is not how they do it. The question is what it means that almost everyone else has forgotten how.